Newton's laws. Newton's laws are very simple, but they can be non-intuitive because we are so used to observing things on Earth. Growing up on Earth, gravity and friction skew our understanding of the true fundamental laws of the universe. That's probably why it wasn't until the 17th century that someone like Isaac Newton came along and figured it out. Okay, so remember on Earth, everything you see around you is being pulled toward the center of the Earth due to gravity. And also, our entire world on Earth is smothered in friction. Okay, friction, remember, comes from the fact that not even not even the smoothest surface you can imagine is perfectly smooth. Okay, so here, any surface you zoom in on is going to have a profile like this. So let's say you have sandpaper or you have ice, smooth ice, like on an ice hockey rink. You might have to zoom in a little bit closer to see this profile in ice, but you're still going to see this kind of a profile. Okay, so when two surfaces are trying to, they're pressed against each other and they're trying to slide, those little surface imperfections are gonna push and pull, slowing those items down, trying to prevent them from moving. Okay, that's why everything you see on Earth tends to slow down and sit still. Okay, air, air. You also have air friction. Air friction. Okay, so let's say you're running, or like shown here, you're driving a car. You throw a baseball in the air, and anything you're trying to move through air. Think of us, we are living in a swimming pool of air, right? Air, anything that tries to move, air is going to try and push on it. Air is going to try and push on it, and also you'll learn in fluids that air tries to stick to things. So the air is sticking to this car and trying to pull the car back. Okay, so we know everything on Earth obeys Newton's laws. Everything in the universe obeys Newton's laws. Well, actually, okay, technically, when you get down to particles on an atomic level, electrons, subatomic particles, your mind gets blown, everything changes. That's quantum mechanics. Go watch those videos. That's why you have physicists, you classify mechanics. You have quantum mechanics that has its own rules. Classical Newtonian mechanics deals with matter on the human size scale, and I believe once you get to like the size of planets, gravity just dominates that. It's like gravitational or planet size mechanics. But we know that everything, all objects in the entire universe that are on the human size scale obey Newton's law. So let's leave Earth. Okay, let's get away from Earth. Let's get away from all that friction and all that gravity, so we can observe how things behave. So we can get a better idea of how things actually behave. Because Earth is confused. Earth, it makes things confusing. So we're out in space, but we want to get way away from Earth. We want to. No, no, no. Let's go way out into empty space, completely away from any planet, any gravitational pull, any other objects or friction. Okay. So, all right, here we are, completely in the middle of nowhere. We brought with us in space a freight liner and a baseball. Imagine the crates here are strapped down nice and tight. So what you have, the ship is a big one bulk piece of mass. Okay. All right. So let's start. What is Newton's first law? Newton's first law of motion. Okay. This is a formal definition I got from the NASA website. I'm not sure if I can say NASA, but okay. So every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. Okay, so this is really simple. All it's saying is that if either one of these masses are sitting down still, they will remain still in their exact position for eternity until an external force comes along and acts on it, and it makes it move. Okay, and in the same light, if if we came in and applied a force to the ball or to the ship and got it moving, then whatever velocity and direction that ship or ball was traveling in, once we released our hands, either one of those masses would move in that exact direction at that exact speed and never slow down for eternity. And no additional power or input would be needed. So you can imagine this ship. If we got this ship moving at 5 miles an hour and let go, then it would just eke along. This big, massive ship would just eke along in that straight line forever, until an external force comes along and makes it change its motion or speed. Okay, so that's it. That's it. Very simple, right? That's Newton's first law. But I think it's confusing because, remember, this, what I just described here. This isn't a playground. We're not at an amusement park playing with the ship and the ball. I mean, this is real life. Space is real life. That's the fundamentals. This is the fundamentals of the laws of mechanics. So you you go outside. Everything you observe outside on Earth is obeying Newton's first law of motion at this very moment. But it's not that intuitive because, like we talked about, gravity and friction, it makes it less intuitive. Okay. Newton's second law just gives you a numerical relationship between how much a mass's velocity or direction will change based on how much force is applied to it. So this relationship is the classic F equals ma, force equals mass times acceleration. You could read this formula in different ways. You could say the force applied to something divided by its mass equals how much that something will accelerate. You could say the force applied to something divided by how much it is accelerating is that something's mass. You could also look at it like, if you observe a quantity of mass accelerating at a certain rate, then you multiply those two values together. The value that you get is the net force being applied to that mass. Okay, so let's look at an example. Say you bring a baby into space, and you get the little boy or girl to push on the ship with its finger. Okay, we're not going to push at the edge of the ship here. We don't want the ship to spin. So what we'll do is we'll have the baby push right at the center of mass of the ship. Okay, so we'll say let's push with 1 pound of force. Okay, 1 pound of force, and the baby will leave its finger pressed for 2 seconds with 1 pound of force and then release. So 1 pound of force and leave it applied for 2 seconds. Okay. So upon release of the finger, the ship is going to be moving. Okay. Well, how fast? Let's see. Okay. Okay. To get to our final speed, our final answer, I'm going to do a bunch of fancy unit conversions with English units. Don't get too bogged down with the details of what I'm doing and saying. I'll make future videos on units and unit conversions. Okay. All right. So let's say this ship weighs 60,000 tons. 60,000 tons. Okay. All right. All right. In English units, Newton's second law. In English units, the law states that if you apply 1 pound of force to a mass of one slug, then that piece of mass will accelerate at 1 foot per second squared. So all these ones are nice. So let's convert our entire situation here to these units to make our lives a lot easier. Okay, so we know that there are 2,000 pounds of weight in 1 ton. So you could say that 60,000 tons is the same thing as 120 million pounds force. I'll put pounds force because there's also pounds mass, right? Okay. Now we also know that the mass of of anything in units of pounds mass is the same numerical value of that something's weight in pounds force. Okay, so this ship has a weight of 120 million pounds force, so we know that means that this ship's mass is, where's my pen? Okay, what the hell is the problem with this thing? Okay, there we go. Okay, so we can say that the ship weighs 120 million pounds. That means it has a mass of 120 million pounds mass. Okay. We know that there are 32.2 pounds mass in one slug. So if you have a slug of something, that means you have 32.2 pounds mass of that something. So you divide this 120 million by 32.2, and we say that this ship, you could say the ship has a mass of 3,729,714 slugs. Okay, so great. Now we've got our full situation here is converted to this nice 1 equals 1 times 1 formula. Okay, so using Newton's law, we say that the baby was applying 1 pound of force to a 3,729,714 slug piece of mass. Okay, so there we go. We know now, this means that in this situation, this ship was accelerating at this value worth of feet per second squared. Feet per second squared. That's what pound force divided by slugs is, a foot per second squared. 1 pound force divided by 1 slug is 1 foot per second squared. Okay, so as long as the baby's finger was on that ship, the ship's speed was increasing by this value of feet per second every second. Okay, well, how many seconds did the ship feel this force, feel this acceleration? For 2 seconds, right? So long the baby's finger was on, was pressed. So let's multiply in 2 seconds. It felt this acceleration for 2 seconds. Okay, cancels out. So now we're going to get the ship's speed upon release of the finger. So let's divide in this 2. Okay, we get 1 over 1, 8, 5, 1, 8, 6, 5, 7. Okay, there is the ship's speed, new speed in feet per second. Okay, but this, what is it? 1 over 1 million feet per second. You can't visualize that, so let's convert this speed to feet per year. I looked it up. There are 31,536,000 seconds in a year. So you multiply that in feet per second. You have 31 million blah 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 seconds per 1 year. Okay, so now let's multiply that 31 million in here, and we'll get our ship speed in feet per year. I'll work this out. This value is 17. So multiply these two in, or divide this big number by this number, you get 17 feet per year. Okay, so there we go. You bring the baby in, the baby applies 1 pound of force with its finger to this 60,000 ton freight liner in space. The baby leaves its finger pressed for 2 seconds, and now the ship is moving at 17 feet per year. It's going to eke along. That's happening. Okay, this is real life. This isn't an amusement park or fantasy land. Okay, this is exactly what would happen if you went into space and did this. Okay, but it's not very intuitive, because on Earth the ship would be sitting in water and it would be being pulled down into the water. So by gravity, and to get the ship to move, you need to overcome that water friction, the water trying to hold on to it, and so it would take a lot more force than just 1 pound to get that ship moving. Okay, let's look at the baseball now. This is really going to make you think. Okay, an average baseball I looked up weighs 5.25 ounces, or which is the equivalent of 0.32 pounds force. Okay, weight in pounds. This means that an average baseball has a mass of 0.00009944 slugs. Okay, so there we go. There's our fundamental units. Okay, so I worked out all these numbers. If the baby applies 1 pound of force to this ball, 1 pound of force for 2 seconds, then releases. Okay, upon release, the ball would be traveling at 200 feet per second, aka 136 miles per hour. 200. Okay, 200 feet per second, 136 miles per hour. Okay, bull, right? Bull. No way. That can't be right. Randy Johnson can only throw a ball 105 miles an hour max. Well, all right. This is what you need to think about. Okay. First of all, you're imagining that the baby approaches the ball being held by an astronaut, and then it presses with 1 pound of force, and then the ball all of a sudden starts moving into space. Okay. Well, in this scenario, the finger would only be in contact for maybe a quarter of a second. So if you did that math, the finger's not holding for 2 seconds, but only a quarter of a second. The ball's final speed would be 25 feet per second, or 17 miles an hour. All right. But like, okay, if you could somehow allow the baby to keep up with the ball as it accelerates, and it's keeping pressing with 1 pound, and you did that for 30 seconds, okay, then upon release, the ball would be moving at 2,200 miles an hour. Okay, so the ball speed is going to increase infinitely as long as there's a net force applied to it. Okay, if you think about Randy Johnson, he torques up his whole body and uses an incredible amount of leverage to apply a lot of force to the ball. But for how long is that force actually being applied and pushing it towards home plate? Okay, well, probably less than a quarter of a second. Okay, and then the ball's speed clocked at 105. That's going to be when it crosses the plate after it's traveled from his hand through 60 feet of air. So it's going to have slowed down a good bit, right? Newton's third law. For every action, there is an equal and opposite reaction. Okay, this is saying that a force on Earth, in the universe, any force you can imagine, never acts alone. A good way to look at this is with forces, there is always two sides to the story. So, so our baby applied 1 pound of force to the ship for 2 seconds, and then we analyzed. Okay, how does the ship react to this 1 pound? How fast does it accelerate, etc. But also, based on Newton's third law, the ship applied 1 pound of force for 2 seconds to the baby in the opposite direction. So let's forget about the ship. Let's just look at the baby. How much is the baby's mass? So this amount of force got applied to it. How fast did it get accelerated in the opposite direction? We could just do a whole other problem now, just like we did for the ship. Okay. So a force never acts alone. For every force acting on a body, there is always an equal and opposite force acting on that body that is causing the force in the opposite direction. Newton's third law, I find, can provide you with a lot of intuition for how components of things are designed in real life. So because of Newton's third law, you can always follow any force to the ground. It's a lot like electricity. For electricity to flow, it needs to be grounded. Well, the same thing with forces. If you can't follow a force to the ground, then it makes no sense. Okay, so let's look at an example. Okay, here we have like a offshore drilling platform. Maybe that's your string going through the ocean to the ocean floor, all the way deep into the ground. Here's a typical tool you might see inside the structure, inside the derrick. They call this a derrick, this structure, exterior structure. So this is a tool you might see inside there, and you can imagine this these teeth here bite on the exterior of pipe. What they do is they bite on a pipe, lift it up, bring it down on top of a pipe that's already in the rig, screw them together, lower the string into the ground, do the same thing over and over again. So these tools are lowering string after string after string deep into the ground. They can hold up. They're designed to hold like 500 tons of weight of pipe string. Okay, so let's kind of look at the inside here. This could be, I don't know what exactly these look like on the interior, but maybe it's something like you got like a bowl. Maybe on the inside it's kind of like I don't know, like a bowl here, and then these teeth are machined out of maybe some plates, right? I mean, there's like these could be more straighter ridges possibly. This could be totally inaccurate. Yeah, I'm sure this is ridiculous looking. But okay, so here's some teeth on these inserts that are gripped onto your pipe. Okay, so we can use Newton's third law. We can start here at our 500-ton string weight, and we can follow this weight using Newton's third law through the teeth, through all the components, sizing components as we go, all the way up through the derrick, through the frame, size components, all the way to the ground. Okay, so look at try and imagine this. Well, the string weight is pulling down on the teeth with 500 tons, and the teeth are machined out of this plate. So the plate kind of in these areas is pulling back up on the teeth with 500 tons. Okay, so we size our teeth, make sure they penetrate deep enough. They have enough cross-sectional area to where they don't shear off, right? Okay, but now let's look at the plate. Well, these plates here, these little inserts, are being pulled down with 500 tons. They're not falling to the ground. They must be being pushed back up by something with a force of 500 tons. So what the bowl is what's pushing back up on them to keep them from falling. Well, Newton's third law, at this point, every force there's an equal and opposite reaction. Well, since these inserts all along the bowl are being pushed up by the bowl with a force of 500 tons, those inserts are pushing back on to the bowl with a force of 500 tons. Okay, so let's design the bowl. Something else is holding that bowl up. The bowl is trying to be pulled down with 500 tons. So what's keeping that bowl from falling? You got to size those components, right? Make sure that these areas don't get dented by that large weight. And you just do this. You can do this on and on and on, component after component, all the way to the ground. You can, that 500 tons here will translate into some forces in your frame here. You just use Newton's third law to follow that load to these points. Okay, so there we go. There is Newton's laws. I hope that gave you a good perspective and understanding of the laws.